So, hello everyone, my name is Subrata Samanta and I am from IIT Kanpur. So, I am your tutor for the physics subjects. So, in the previous class, we will discuss how to calculate the electric field on a axis of a rod and the perpendicular bisector of a rod. Okay, and I hope you calculated the electric field that is given in the previous class. So, let us draw once again the picture. Okay. So, this one is the x axis and this one is the y axis, and if we put a rod of length L on the x axis, okay, and the center at the origin. So, let us, this one is O, the origin, and the length of the rod becomes L, right, and we calculate the electric field on the y axis at a point P. Okay. The distance from the center of the rod, the perpendicular distance is becomes y. Okay. And this is the, let us say y hat x hat. Okay. So, and so how to calculate? Now we consider a small strip on the rod, okay, and then so the angle from the y axis is theta prime, okay, and the distance is r prime, okay, this one is the x prime, okay, and this the length of the strip is dx prime, okay. So, then we can calculate integrate it over the length of the rod, we get the expressions, and I hope you also verify this one. So, E y 1 over 4 pi epsilon naught times 2 lambda sin theta over y, right. Theta 1 is the angle, the end point of the rod making an angle at a point P is theta. Okay. So, this one is theta. Okay. So, the end point of the rod making an angle theta, and due to the symmetry of the rod, so this one is also, this the left hand point of the rod also makes an angle theta, okay, because we put the center of the rod at the origin. So, then the y component are only non-zero. So, and the x component become cancel each other, right. So, the net electric field in the y direction. So, only y components are non-zero and E x becomes 0. Okay. So, the net electric field in the x directions become vanishes. So, now we put the sin theta value. So, we know that the sin theta, so this one distance is L by 2, okay. So, L by 2 divided by square root of, so this distance is y, right. So, y square, the perpendicular distance, plus L by 2 square, right. So, now if we take the limit where this distance y is very greater than equals to L. So, limiting case 1. So, where y is very greater than L, right. So, that means the L, the length of the rod, and y is the perpendicular distance, okay, the bisector of a rod. So, in the limit of y very greater than L, so the above expressions, then how, so you write that y square plus L by 2 whole square is nearly equals to y square, right, because the y square is dominant. So, then the electric field E y becomes 1 over 4 pi epsilon naught 2 lambda over y times L by 2 over y. So, this one becomes 1 over 4 pi epsilon naught lambda L over y square, right. So, this lambda L nothing but the total charge of the rod, right. So, if you calculate the total charge of the rod, because the lambda is the linear charge density. So, lambda is the linear charge density and the total charge q, okay. So, since it is a uniform charge density, so we take over the lambda outside of the integral and then dl, okay. So, this becomes a length, so lambda times L, right. So, if we plugging into this value in the expressions, okay. So, the expressions of the E y becomes 1 over 4 pi epsilon naught q over y square, right, where the q is the total charge. So, the system is looks like, so then the system is looks like a point charge. Okay. So, when we observe at a distance very greater than equals to L, the length of the rod. Okay. So, from that point the system whole system looks like a point charge with total charge q. Okay. So, this is the electric field due to a point charge, electric field due to a point charge with total charge q, right. So, now if we consider the other cases, okay, where so case 2, so where L is very greater than y, right. So, the length of the rod becomes large in comparable to the distance where we calculate the electric field, okay, the perpendicular bisector of a rod. So, in that limit, so which one is dominant? So, y square plus L by 2 square, this become L by 2 square, right. So, in the expressions E y, so if we look into these expressions again, so this one, okay. So, 1 over 4 pi epsilon naught 2 lambda over y. So, this E y becomes 1 over 4 pi epsilon naught 2 lambda over y, okay, and L by 2 cancel. So, we put L by 2 and there L by 2 dominant part. So, this thing cancel. Okay. So, only left this, okay. So, this is again nearly equals to, right. So, we use this symbol that nearly equal, okay, approximate, it is not a nearly equal, it is approximate value, because we are considering a limiting case, it is not a exact. So, again, so what is this mean? That means if we consider a infinite length, okay, of a rod, okay, and we calculate the electric field, the bisector, perpendicular bisector at any point in the perpendicular bisector of a rod, okay. So, we get this. So, the later in the most probably in the next class, okay, we will calculate the electric field from a infinite cylinder, okay, using Gauss law. So, we see that this is the expressions due to a cylinder, okay. So, this basically, so in this infinite length limit, this infinite length limit. So, here infinite means that we are considering a large value of L, okay. So, in this infinite length limit, the system has cylindrical symmetry, the system has cylindrical symmetry, okay, and that is the expressions. So, this one is the expressions of an electric field, okay, the perpendicular axis of a cylinder, okay. So, we will calculate these details in a next class for a cylindrical object, how to calculate the electric field using Gauss theorem, okay. So, it is easy to and straightforward to calculate, okay. So, now if you plot this thing, if we plot the E y, so if we plot E y as a functions of y, okay, yes. So, basically we plot E y as a functions of y by L and E y by E naught, okay. So, dividing by the same dimensions such that this y by L is a dimensionless and E y by E naught is also dimensionless. So, E naught is just the q over 4 pi epsilon naught L square, right, since L is a constant, okay, the length of the rod. So, we divided by this, and also the perpendicular distance is also divided by the length L. So, make this variable as a dimensionless. So, the plot is looks like this, sorry, it is not negative. So, it looks like this. Similarly, for, okay, so because of symmetry, So, this because of symmetry, so it symmetrical around the origin. Okay. So, this one is the origin, is symmetrical around the origin. Okay. Okay. So, in the next we calculate the electric field due to an arc. Okay. So, let us say consider a thin rod. So, another example is that so a thin rod with a uniform charge per unit length lambda, okay. So, is bent into the shape of an arc of a circle, is bent into the into the shape of an arc of a circle of radius r, right. And the arc subtended by a total angle 2 theta naught and symmetric about the x axis. So, I have not written and just draw the picture. Okay. So, what is tells basically. So, if we draw x axis and y axis and we consider a arc, okay. So, this arc symmetry about the x axis, okay, and the subtended angle total angle 2 theta naught. So, that means the end point of the arc makes an angle 2 theta naught, okay. Okay. Since this one is symmetric about the x axis. So, the angle from the x axis is theta naught this side and this side is also theta naught, okay, such that the total angle is 2 theta naught, okay, and symmetry about the x axis. So, symmetry about the x axis. So, whenever you are solving some problems, so you first consider what kind of symmetries are there, okay, because they simplify the problems, okay, to solve. Yeah. So, now we calculate the electric field at this point. So, we denote it. So, this point let us denote this P or origin O, okay. So, at O, that means the origin, we calculate the electric field due to this charge distributions, okay, over an arc of a circle, okay. And the radius denoted, that is r, okay. So, the radius of an arc, okay. So, then we again makes an so makes a small strip on the arc. So, let us consider the strip here, okay. So, these strips again the distance from this point to this, the distance from the same origin is r, since the radius, okay. So, this one is fixed and the angle is let us say theta, okay. So, at distance at angle theta from the x axis, we consider a small strip, okay, with a charge dq, okay, and the radius is r, okay, because this one is fixed. So, the length, the differential length of this small strip dl, okay. So, this is the length, okay. So, consider a differential element of length. So, differential elements of length dl, this becomes r d theta, okay, and the angle d theta is that this one, okay. So this is the d theta, and the dq, the charge of the small strip dq. So let us say this one is dl, and the dq, the charge of the charge of a small strip is lambda times dl, okay, because lambda is uniform charge density, okay, that is given in the question. So now put the values of dl, so lambda r d theta. Now we calculate the electric field at a point O due to this charge dq. Okay. So the contributions to the electric field at O due to this charge dq. So the electric field at O origin due to charge dq, okay, h dE, again the differential, okay, dE equals to 1 over 4 pi epsilon naught, okay. So dq over r square with r cube. So this is the general form. Now we put what is r here is capital R, right. So here the distance is 1 over 4 pi epsilon naught dq over r square, right. So basically the distance is capital R, the radius of an arc, okay, and times the r cap, right. So here the r cap is that, so if we draw a electric field lines at point O is in this direction, right. So this is theta, this one is also theta. So now we split into the I cap and j cap, okay, they are projected into the x axis and y axis. So this r cap becomes cos theta minus cos theta I cap minus cos theta I cap minus sin theta j cap, right, because this one is the electric field vector dE, right. So we projected this or this, right? So both are negative directions, right. So this one is dy cos theta and this one is, so this one is dy sin theta. So the j cap direction the sin theta component, right, and in the x cap direction cos theta. So now I hope it is clear now. So then we can calculate the total electric field due to arc, okay. So that means we integrate the theta from a minus theta naught to plus theta naught, right. So because we consider the anti-clockwise for plus sign and the clockwise is minus sign, right. So the net electric field at point O electric field at point O is, so E, so integrate over 1 over 4 pi epsilon naught lambda by r, right. So now put dq equals to lambda times r d theta minus theta naught. So the limit is important, minus theta naught to plus theta naught, okay. So since that this is in the clockwise directions and this one is the anti-clockwise directions, so that is why you put a minus theta naught. So we go in one direction, okay, and this d theta times minus cos theta I cap minus sin theta j cap. So if we calculate this, okay, we finally got, and this one is check u, okay. So 1 over 4 pi epsilon naught times 2 lambda sin theta naught by r times I cap. So there is a no j cap component, okay, because the sin theta d theta is vanishes because the integral is symmetric, okay, around 0. So you verify this and this results, okay. So we will interpret this result in the next class, okay, and in the meantime you must verify this result, okay, by doing some simple integral, okay. So we will see in the next class. Thank you.